Hello, I'm Sophia Catrick, and this is my video for Professor Dunlap's Physics 212 class. I'm going to start my video with something fun and easy. Ohm's law. It's the best law because it's simple. I'm going to start by showing what happens when you put resistors in series versus in parallel. We're going to start with series, and as we know in series circuits, the equivalent resistance is the resistance of each resistor just summed up. And the current will be equal, and the voltage drops across each resistor will not be equal, unless, of course, the resistors are all the same resistance, which they are in this case. So for resistors, I've got these light bulbs, which I've measured with my multimeter for resistance, and they're about 70 ohms each. So I've added them together, or multiplied by 3, because they're in series. So that becomes 216 ohms. And then I've got 18 volts. I've got two 9-volt batteries here, and they're hooked together. And so the current going through here should be 0.038 amps. And that current is the same in all the resistors because they're in series. So of course we would expect them to all be the same brightness. This is something I'm glad I'm doing because I always get this wrong. So we plug it in, and we have 3 light bulbs. They all look about the same amount of brightness. Although the voltage drop across
A good way
each
to
one
check
of
and
them
make
is
sure
going to
that
be different. You've got correct voltage drops across each resistor is to make sure that they add up to the equivalent voltage. So I'm going to check the voltage across each resistor in parallel, of course, because I'm measuring voltage. So I'm going to measure each one, and each one I'm getting about 5.7 volts. And when you add that up, that's almost 18 volts. We've lost a little bit of voltage there. But normally in series, we would not have the same voltage drop across each resistor. But because these light bulbs are all the same resistance, we do in this case. Now I've set up a parallel circuit, and I've got my one resistor coming off my 2 batteries, my 18 volts, and then I've got 2 in series here that are coming off from the first one in parallel with the first one in series with each other. And I've drawn the schematic of what's going on here. I've got my 1 resistor here, and then I've got my 2 in series and in parallel with this one and my 18 volts. And so when I plug in my circuit, you can see that this 1 battery here, or the 1 resistor, the light bulb here, is much brighter than these other 2, and they are about the same brightness, dimmer than this one, which we expect because this light bulb has way more current in it than these 2. Because when the current comes out of the battery, it can either go across this light bulb or it can go through these 2. So as we know, the equivalent resistance in parallel, once I add these 2 together in series, is the inverse of 1 over these 2 added together, plus this one, 1 over this one, and we get 48 ohms as the equivalent resistance. Now, we can see mathematically that in this one, we have 18 volts and 72 ohms, so we get 0.25 amps of current. And in these 2, current being the same in series, they each have 18 volts equals 144 ohms times I23, and we get that to equal only 0.125 amps, so we can see why these are dimmer. And of course, the current in this one equals, plus the current in this one equals the current in the system, which is 0.375 amps. So now we have seen series and parallel circuits. and we'll get on to the fun stuff, which is capacitor discharge. For this section of my project, I'm going to talk about capacitors, which are used for everything from taking the noise out of DC circuits to storing energy for a camera flash. And as we know, when you charge up a capacitor, charge over time equals the capacitance times the voltage in the battery times the product of 1 minus E to the C to the T minus T over RC, as you can see here. And for charge up, I have a 9-volt battery, I have a 1 farad capacitor, and I have a 330 ohm resistor. And even though you can't see it, you have to trust me, it's there. And for discharging the capacitor, I'm going to use the same 1 farad capacitor. And I'm going to use this light bulb, which we have to use the multimeter to find the resistance in before we're able to take that charge up, because as we know, once we charge up a capacitor, that charge is the Q naught for discharge. So we have the charge over time for discharge is Q naught times E to the negative T over RC. And the resistance this time will of course be different. It'll be the resistance in this light bulb. And then we're going to measure current over time, which is this equation here, the negative Q naught over RC times E to the negative T over RC. And the current will decrease and eventually reach a limit where it's nearly zero, as well as the charge. And we're going to see that happen because we're going to see the light bulb light up with the capacitor hooked up to it like a battery, and over time the light bulb will go out. And we're going to see the charge and the current in real time on the serial monitor of my computer as it runs the code that runs these two equations. So the piece that we need before we can start charging and discharging the capacitor is the resistance in this light bulb. So I've hooked it up to my multimeter with the leads for the positive and negative side, although resistors don't have that. And I've got it set to measure ohms up to 200, and it is looking like, if we can get it to actually show, well, I'm reading 7.3 ohms. So I'm going to go ahead and put that into my program. 7.3 ohms, and that will be for discharge. For charge up, I'm going to take my battery, and I'm going to use just some regular alligator clips to hook it up. I'm going to hook it up to my resistor. And then to one side of my capacitor. So in this tangled mess, we've got resistor here, and we've got the capacitor down here, and we've got the 9-volt battery. So as soon as I hook up the other lead of the battery, we will be charging. Okay, so we've got this nice little circuit here, and I've discharged my capacitor, I've hooked everything up, and I have my program ready to take the time measurements and the charge measurements as it charges up. I'm going to use my Arduino breadboard to get those measurements. So I'm going to go ahead and get that code running, and when it gives me the countdown, I will hook up to the battery. And we're ready. So that's charging up, and I'm going to go ahead and disconnect. And we can see that while it was connected, it's hard to show everything at once. While it was connected, we were getting time and charge measurements. And the last one we got before I disconnected it was time 15.02 seconds and a charge on the capacitor of 0.4 coulombs. So those are what I'm going to go over here and make sure those are the values that are in my discharge for Q naught. I'm going to have 0.40, and we should be good to go on this one. And next we will do the discharge. All right, we are all ready for capacitor discharge. I've got my light bulb and my capacitor that's all charged up. And as soon as my program gives me the countdown, I will plug in the other lead and we will watch it discharge. Okay. All right. Okay, we are at current 0.05, 04, 3, 2, 1, and now we've hit 0. We still have a little glow there. I suppose no experiment is perfect. I've run this one a few times and you always end up with a little glow after the 0 mark. I'll have to calculate my percent error. But as you can see with the code, you can see the time, the charge, and the current, which has now gone to 0. Looking at this data, the light bulb was still on when my calculations went to 0. They went to 0 at 18.06 seconds, and the capacitor did not stop discharging until 23.07 seconds, which makes that about a 27% error. That's been about the average all the times I've run this experiment, and of course no experiment is perfect. So that is the end of my video, the end of my project. Thank you for watching. I hope you enjoyed it. Bye.